Hey guys, in this video we will talk about collision detection techniques and algorithms. We are presenting you this video as in group 2 whose group members are Ajay Kumar, Ritik Kumar and me Saksham Bharti. So let's first talk about the contributions. So Ritik Kumar has worked on narrow field detection techniques, Ajay Kumar has worked and prepared his data on separating access theorem, and I have worked on broad field detection. So first, let me give you the overview of this video. So first, we will introduce you the collision detection. Then I will introduce you with broad face detection, including KD trees. Then my friend Ritik will tell you about the narrow face detection techniques, including GJK algorithm, which is very important. And then my friend Ajay will tell you about continuous detection, which is separating access theorem. So let's start so in simulations and games, think since so in simulation and game, we need to figure out when two or more objects collide. So here a question arises like why we need to know that the two or more objects are colliding. So think like you're driving a car in a game and your car struck your collides with a wall. So there must be some destruction when two objects are colliding. So to do that destruction, the game needs to know. So here it becomes important to detect where two or more objects are colliding. But doing this check, the collision check, or for every frame of the game can be very much computationally expensive. So to reduce that expensiveness of that computation, we use two-step approach, which is first is broad face detection and next one is narrow face detection. So first, let us talk about broad face detection. So it is the first layer where the identifying pairs of that objects, the identifying pairs which may collide or which have the potential of colliding are identified. So consider it like the broad face detection doesn't check for the original collision, but it's narrow down the objects which may collide. So think of it like filtering through a list of potential suspects before doing a detailed investigation. This step is very crucial. Like this step become very crucial for large games where checking every possible pair of object become very much computationally expensive, especially when there are thousands of objects in a frame. So broad face detection help us by ruling out pairs which are not even close of colliding. So where a question arises why it is very important. So, well, as I mentioned, the collision detection can be very expensive. So, if we tired of checking collision between all the objects at a time, so it may slow down our process. So, broad face detection simplifies the things, narrow down which objects to check. So this saves our very much resources, like as I have mentioned, like Broadfish reduce the number of pairs for detailed checks and saving our times and resources. So one of the most important, what happened? So one of the most uh, used data structure is KD trees. So here comes what are KD trees? So KD trees are data structures uh, using broad face detection to organize and divide space efficiently. So imagine you are in a huge 3D world with lots of objects. A KD tree divides the space into small regions using axis aligned planes like uh, um, axis aligned planes. Like think of it like space slicing your around in three x, y, and z axis. Each node in the tree represents a region in which space in represents a region in a space, and as you go deeper into the tree, the space divided more finely. Like if you go down the tree, that is region is more finely divided. So the idea is to organize the objects in such a way that you need to check a collision only for those nodes which are near to each other in the position uh, in the tree, like in the tree where those are like near to each other. So with what are the steps, like how we use KD trees in broad phase detection? So first, we build a KD tree using a bounding boxes of the objects in the scene. These boxes are like containers around the objects. Next, we query the tree to find the pairs of objects that are near to each other, and only these pairs are passed to the narrow phase, passed to the narrow that I say pass to the narrow phase for the more detailed collision check. By using KD trees, we can efficiently prune or eliminate irrelevant pairs, uh, which makes uh, which makes which makes the system more efficient. The tree scales well for this tree. Like this tree works very well for the large and complex environments and handle high dimensional data efficiently. This makes it perfect for games and simulations where space and objects are constantly changing. So, in the conclusion, I will. So, the summary is like the broad phase collision detection is essential for performance optimization. That I tell you, it is very much expensive, competition expensive for checking every possible pair. The KD tree provides an efficient method for spatial partitioning and reduce unnecessary collision checks, and that is the broad phase detection do's. So key takeaways are like by using KD trees, we focus computational efforts only on objects that are close to each other, whose closeness is determined by their position in the KD trees, making the process more scalable for complex systems. Thank you. Next, my friend will tell you about the narrow phase detection. Thank you.
Hi everyone, my name is Ritu Kumar and today I am going to present a topic which is a part of the collision detection. So basically, the topic is narrow phase detection. Earlier we have studied about broad phase detection in which we found about how two objects collide. Now here in narrow phase detection we will get to know in deeper insight about really the two objects are colliding or not by the help of some algorithm and computation. So for this narrow phase detection, we take the help of GJK algorithm, and many more algorithms are there, but it is the most efficient algorithm till now. So it is named after its three authors, Gilbert, Johnson, and Kirthi. So uh, let's dive the into the JGK algorithm. So before studying JGK algorithm, let us know that there are 2 to 3 main component of this algorithm: the Minkowski difference, support function, the simplex. So it basically it is these functions are used to calculate the JDK algorithm, which basically helps to find the objects collision. So here we have two steps: the convex polygons, the A and B. We can see by the help of our eyes and say that these two objects are colliding, but how will computer get to know that if these objects are basically colliding or not? So in order to get that insight for the computer, we take the help of these algorithms. So here we are looking in a shape which is known as simplex, which we will get to know in later slides. So this shape is simplex. Now the algorithm says that the JDK algorithm says that if the origin lies inside this simplex, then we can say that these two algorithms means these two objects are colliding basically. Now we will see the difference, means the Minkowski difference, which is this part, this highlighted part. If the origin comes in between, the concept of origin is basically that if the points difference is getting to zero, means both are colliding. So let us first see what is a support function. So support function is used to find the furthest point from the um, shape. Here the shape is a triangle, but we are let's consider it to be the quadrilateral, which was our original shape. So it finds the furthest point in the from the shape to the simplex, which basically helps in finding the separating axis, which is intermediate method or intermediate step in finding the Minkowski difference. So now after the support function, this is the simplex. So there the simplex had uh, an ambiguous shape. So we will convert or break them into chunks of any shape of polygon, basically a convex polygon, which is uh, in which we will take in our ease in a way to compute our problem. So here we have broken them into pieces of triangles. Now, in the piece of triangle, if the origin lies in between this triangle area, then we will say that these two shapes are really colliding, and if the origin fails to lie in the area covered by the this polygon, or basically a triangle which we have defined, then we will say that these two objects are not colliding clearly. So this is the use of simplex.
Good evening. My name is Ajay, and in addition to my teammate has talked about collision detection technique, I am going to explain how separate axis theorem help in 2D collision detection. So first we will talk about what is separate axis theorem. Separate axis theorem states that if we can find an axis that separate two shapes, they are not touching. If no axis separate the two shapes, then the shapes are colliding. Here in this example, we can see an rectangle and a pentagon, and we can draw a axis that separate the two shapes. Now, let's talk about how we can apply separate axis theorem to rectangle. In rectangle, in simple, we can check x and y axis to detect if shapes are touching or not. In case of rotated more complex shapes, we have to calculate minimum and maximum value along the rotated axis by projecting points onto the axis. Use projection to check separation. We can understand this by looking this example. Here we have a box 1 and box 2 and projection of box 1 and projection of box 2. We can see both are overlapping in both x and y axis. And when we take projection on the rotated axis, here we can see in green color projection of 1 and projection of 2. There is a gap between both projection, and we can easily draw a line that separate the box 1 and box 2 toward that rotated axis. So this was the explanation of how we use in complex shapes, and we have to take projection on the rotated axis to determine whether an axis lies or not. But how we can handle if we get other kind of shapes? Here we have an triangle and a pentagon. So in this case, we have to use as normal to find the axis, and we have to check all the possible axes to find whether any axis lies or not. And in case of convex shapes, we have to decompose convex shapes into convex shapes to check collisions. So this was the my part. Thank you.